the European Space Agency has released a startling new image of the interstellar object 3I Atlas, captured by the Janus camera aboard the JUICE spacecraft. From a distance of approximately 66 million kilometers, the image reveals something that defies the fundamental expectations of cometary physics: jets of gas and dust streaming toward the sun. The image is not a mere snapshot. It is a portrait of a phenomenon that raises questions about the physics of cometary outgassing, the nature of interstellar objects, and the limits of our understanding. The Janus observations represent the first close-up view of 3I Atlas in the inner solar system from a spacecraft vantage point, capturing over 100 images that document the strange geometry of the jets and their relationship to the sun. The jets themselves extend far from the nucleus, yet instead of trailing behind, they align in a direction that appears almost deliberate, pointing sunward as if defying the expected physics of sublimation and solar pressure. While Earth-based telescopes have observed the object from afar and amateur astronomers have noted unusual tail structures, the ESA images provide unprecedented clarity, showing the anti-sunward orientation with remarkable resolution. Overlays in the released images indicate both the sun's position and the trajectory of 3I Atlas, making it unmistakable that these jets do not conform to typical cometary behavior. The spacecraft's unique position, far from Earth and in a geometrically favorable orientation, enable these observations, providing a rare perspective that ground-based instruments simply could not achieve. The dataset returned from the JUICE spacecraft includes more than just images. Instruments aboard the spacecraft, including spectrometers, ultraviolet sensors, and particle detectors, captured information on the composition and behavior of the coma and jets, allowing scientists to begin disentangling the physics behind these anti-sunward features. While the full analysis of these data is ongoing, preliminary observations confirm that the jets are not optical illusions or artifacts of imaging. They are real structures of gas and dust behaving in a manner that challenges conventional comet models. Earlier measurements from the Hubble Space Telescope suggest that the nucleus of 3I Atlas is approximately 2.6 kilometers across, larger than its interstellar predecessors. Yet these jets display a precision and persistence that is rare even among solar system comets of comparable size. For scientists observing these images, the implications are immediate. The mechanisms driving these jets may involve processes beyond simple solar heating, potentially including rotational dynamics, subsurface volatiles released in atypical patterns, or other unknown effects that control the directionality of ejected material. While these observations have generated intense interest, they are part of a larger story. Long before the November 6 images, 3I Atlas had already demonstrated a series of peculiar behaviors that set it apart from known comets. Its trajectory through the solar system, its spin orientation, and its jet activity have repeatedly challenged astronomers, prompting a systematic analysis by Harvard astrophysicist Avi Loeb, who categorized 18 distinct anomalies. Rather than viewing each unusual observation in isolation, Loeb organized them into a comprehensive framework, highlighting patterns in geometry, composition, and dynamics that suggest 3I Atlas consistently behaves in ways atypical for a natural comet. The first 9 of these anomalies focus on orbital and geometric peculiarities, revealing a level of structure and directional consistency that seems improbable for a purely random interstellar visitor. The object's orbit itself is striking. Unlike the chaotic paths often associated with interstellar objects, 3I Atlas entered the solar system on a retrograde trajectory that is aligned remarkably closely with the plane of the ecliptic, within approximately 5 degrees. For an object originating from a random direction in the galaxy, this near-ecliptic alignment is statistically improbable. Its encounters with the inner planets are similarly unusual. 3I Atlas passed near Mars and then Jupiter, a series of encounters that, combined with its path behind the Sun, created observational constraints that seem almost convenient. Loeb highlights that its closest approach to Jupiter coincides nearly with the planet's gravitational influence boundary, a geometrical coincidence that further emphasizes the object's precise and unusual trajectory. These features, while not impossible, suggest an orbital structure that is atypical for interstellar objects known to date. Even more remarkable are the patterns of jet activity. Before perihelion, 3I Atlas exhibited a long, tightly collimated jet pointed toward the Sun, a stark inversion of expected cometary behavior. Its spin axis was also oriented nearly toward the Sun, reinforcing the improbability of the observed jet alignment. The jet itself appeared to wobble slightly, implying an origin near the rotational pole of the nucleus, a configuration that would require finely tuned geometry. Similar jets reappeared both before and after perihelion, suggesting a persistent directional mechanism rather than a transient outgassing event. Advanced image processing further revealed 3 smaller jets arranged roughly 120 degrees apart, implying symmetrical activity around the nucleus. While some jets originated from the night side of the object, in darkness, defying models in which sunlight alone drives sublimation. Each of these anomalies, taken individually, might be dismissed as curious, but together they paint a picture of an object whose activity is both persistent and directed, raising fundamental questions about the forces shaping its behavior. Beyond these geometric anomalies, 3I Atlas exhibits a set of physical and compositional peculiarities that amplify the mystery. Among the latter 9 anomalies identified by Loeb, several relate to material properties and observed emissions. The angle of trajectory deflection corresponds intriguingly to the opening angle of the antitail, a geometric coincidence that appears improbable. Observers noted a precise alignment of the antitail with Earth's perspective, a momentary configuration that underscores the unusual spatial dynamics of the object. Additionally, the direction of 3I Atlas's approach is reportedly within 9 degrees of the location of the famous 1977 WOW radio signal, a fact that is sparse speculation but remains anecdotal. Chemically, the gas surrounding the nucleus contains an elevated nickel-to-iron ratio, with dust particles larger than typically seen in cometary jets, potentially explaining their ability to resist solar radiation pressure despite their sunward direction. Spectral measurements suggest changing molecular compositions, with icy fragments visible before perihelion giving way to organic molecules and water spikes afterward. The nucleus itself is massive relative to previous interstellar visitors, traveling at higher speeds, and polarimetric studies indicate extreme negative polarization of reflected light. Finally, the object brightened rapidly and exhibited a bluish hue compared with the Sun, highlighting differences in scattering and particle properties that further distinguish it from typical comets. Collectively, these 18 anomalies underscore the unique nature of 3I Atlas and fuel ongoing scientific debate about its origin and behavior. These observations, when combined with the dramatic anti-sun jets captured in the November 6 Janus image, suggest that 3I Atlas may challenge conventional cometary theory. While natural explanations remain plausible, including unusual rotational dynamics, subsurface structures, or atypical dust properties, the coherence and repetition of these features make it a singular case study. The anti-sunward jets, in particular, highlight how a single object can confront multiple expectations of physics simultaneously, from outgassing directionality to particle size and composition. This makes 3I Atlas not only a target for detailed observation, but also a natural laboratory for understanding the limits of our current models for comet behavior and interstellar object dynamics. Looking ahead, March 16, 2026 represents a key observational milestone. On this date, 3I Atlas will make its closest approach to Jupiter, offering another opportunity for high-resolution imaging and spectroscopy from existing spacecraft and Earth-based instruments. Scientists anticipate that this encounter will provide additional clues about the mechanics of its jets, the structure of its coma, and the composition of the nucleus. Will the anti-sunward jets persist, revealing a consistent pattern, or will the object display new, unexpected behavior? Will subtle geometric coincidences observed previously hold, or will natural dynamics explain them? The answers remain uncertain, but the anticipation is palpable. Every observation of 3I Atlas adds a piece to a puzzle that sits at the boundary between known comet physics and the broader mysteries of interstellar space. By March 16, scientists hope to clarify whether the anti-sun jets represent a fleeting anomaly, a reproducible physical mechanism, or a broader pattern among interstellar visitors. Whatever the outcome, 3I Atlas stands as a symbol of the unknown, a celestial emissary from another system, behaving in ways that stretch our understanding and demanding close attention. Its sunward jets, geometric peculiarities, and compositional quirks are a call to rethink assumptions and refine models, while also celebrating the rare opportunity to study a truly interstellar visitor in real time.